In a craft with a pusher configuration, the propeller are mounted behind the respective engine. According to British aviation author Bill Gunston, a pusher propeller is one mounted behind the engine, so that the drive shaft is in compression. Pusher configuration describes this specific thrust device attached to a craft, either aerostat or aerodyne or others types such as hovercraft, airboat and propeller-driven snowmobiles. Pusher configuration also describes the layout of a fixed-wing aircraft in which the thrust device has a pusher configuration. This kind of aircraft is commonly called a pusher. Pushers have been designed and built in many different layouts, some of them quite radical. History. The rubber-powered Plano 4, designed by Alphonse Pénaud in 1871, was an early successful model aircraft with a pusher propeller. Many early aircraft were pushers, including the Wright Flyer, the Santos Dumont 14 bis, the Voisin Farman R and the Curtiss Model D used by Eugene Ely for the first ship landing on January 18, 1911. Henry Farman's pusher Farman 3 and its successors were so influential in Britain that pushers in general became known as the Farman type. Other early pusher configurations were minor variations on this theme. The classic Farman pusher had the propeller mounted behind the main lifting surface with the engine fixed to the lower wing or between the wings, immediately forward of the propeller in a stub fuselage called a nacelle. The main difficulty with this type of pusher design was attaching the tail. This needed to be in the same general location as on a tractor aircraft, but its support structure had to avoid the propeller. The earliest examples of pushers relied on a canard, but this has serious aerodynamic implications that the early designers were unable to resolve. Typically, mounting the tail was done with a complex wire-braced framework that created a lot of drag. Well before the beginning of the First World War, this drag was recognized as just one of the factors that would ensure that a Farman-style pusher would have an inferior performance to an otherwise similar tractor type. The U.S. Army banned pusher aircraft in late 1914 after several pilots died in crashes of aircraft of this type, so from about 1912 onwards the great majority of new U.S. land plane designs were tractor biplanes, with pushers of all types becoming regarded as old-fashioned on both sides of the Atlantic. However, new pusher designs continued to be designed right up to the armistice, such as the Vickers Vampire, although few new ones entered service after 1916, at least up to the end of 1916. However, pushers were still favored as gun-carrying aircraft by the British Royal Flying Corps, because a forward-firing gun could be used without being obstructed by the arc of the propeller. With the successful introduction of Focker's mechanism for synchronizing the firing of a machine gun with the blades of a moving propeller, followed quickly by the widespread adoption of synchronization gears by all the combatants in 1916 and 1917, the tracked configuration became almost universally favored and pushers were reduced to the tiny minority of new aircraft designs that had a specific reason for using the arrangement. Both the British and French continued to use pusher-configured bombers, though there was no clear preference either way until 1917. Such aircraft included the Voisin bombers, the Vickers F.B.5 Gunbis, and the Royal Aircraft Factory F.E.2. However, even these would find themselves being shunted into training roles before disappearing entirely. Possibly the last fighter to use the Farman pusher configuration was the 1931 Vickers Type 161 Cow Gunfighter. During the long eclipse of the configuration configuration. The use of pusher propellers continued in aircraft which derived a small benefit from the installation, and could have been built as tractors. Biplane flying boats had for some time often been fitted with engines located above the fuselage to offer maximum clearance from the water, often driving pusher propellers to avoid spray and the hazards involved by keeping them well clear of the cockpit. The Supermarine Walrus was a late example of this layout. The so-called push-pull layout, combining the tractor and pusher configurations, that is, with one or more propellers facing forward and one or more others facing back, was another idea that continues to be used from time to time as a means of reducing the asymmetric effects of an outboard engine failure, such as on the Farman F-222, but at the cost of a severely reduced efficiency on the rear propellers, which were often smaller and attached to lower-powered engines as a result. By the late 1930s, the widespread adoption of all-metal stress-skiing construction of aircraft meant, at least in theory, that the aerodynamic penalties that had limited the performance of pushers were reduced. However, any improvement that boosts pusher performance also boosts the performance of conventional aircraft, and they remained a rarity in operational service, so the gap was narrowed but was not closed entirely. During World War II, experiments were conducted with pusher fighters by most of the major powers. Difficulties remained, particularly that a pilot having to bail out of a pusher was liable to pass through the propeller. This meant that of all the types concerned, only the relatively conventional Swedish Sub-21 of 1943 went into series production. Other problems related to the aerodynamics of canard layouts, which had been used on most of the pushers, proved more difficult to resolve. One of the world's first ejection seats was designed for this aircraft, which later re-emerged with a jet engine. The largest pusher aircraft to fly was the Convair B-36 Peacemaker of 1946, which was also the largest bomber ever operated by the United States. It had 6 3,800 horsepower Pratt & Whitney Wasp major radial engines mounted in the wing, each driving a pusher propeller located behind the trailing edge of the wing. Although the vast majority of propeller-driven aircraft continue to use a tractor configuration, there has been in recent years something of a revival of interest in pusher designs. In light home-built aircraft such as Burt Rutan's canard design since 1975, ultralight such as the Quad City Challenger, flexwings, paramotors, powered parachutes, and autogyros. The configuration is also often used for unmanned aerial vehicles due to requirements for a forward fuselage free of any engine interference. Engine installation considerations. In a pusher configuration, the force provided by the propeller is pushing towards the engine, rather than away. To convert a tractor engine and propeller combination to pusher operation, it is not sufficient to simply turn the engine and propeller round, since the propeller would continue to pull, driving the aircraft to the rear. Assuming the engine cannot be run in the reverse direction, the handedness of the propeller must be reversed. The loads on the thrust race are also reversed, because the pusher propeller is pushing into the engine rather than pulling away from it as in a tractor. Some modern engines designed for light aircraft are fitted with a thrust race suitable for both pushing and pulling, but others require a different part depending in which sense they are operating. Power plant cooling design is more complex than for the tracked configuration, where the propeller forces air through the system. Configurations. Aerostatic airships are the oldest type of pusher aircraft, going back to Frenchman Henry Giffard's pioneering airship of 1852. Aerodyne pusher aircraft have been built in many different configurations. In the vast majority of fixed-wing aircraft, the propellers are still located just behind the trailing edge of the main lifting surface, or below the wing, with the engine being located behind the crew position. Conventional layout. Conventional aircraft layout have a rear tail for stabilization and control. The propeller may be close to the engine, as the usual direct drive. The propeller may be ahead of the tail, inside the framework, in line with the fuselage, between tail booms, above the fuselage, on wing, on nacelle or axial pod, or coaxially around rear fuselage. The propeller may be located behind the vertical tail, under the horizontal tail. Engines and propellers may be located on wings or on lateral pods. The engine may be buried in a forward remote location, driving the propeller by drive shaft or belt. The propeller may be located ahead of the tail, behind the wing or inside the airframe. The propeller may be located inside the tail, either cruciform or ducted fan. The propeller may be located at the rear, behind a conventional tail, a T-tail, an inverted V-tail, a Y-tail or a cruciform tail. The propeller may be located above the fuselage, such as a glider with a retractable propeller. Canard layout. In canard designs, a smaller wing is present at the front of the aircraft. This class mainly uses a direct drive, either single-engine, axial propeller, twin engines with a symmetrical layout, or an inline layout, as the famous Rutan Voyager. Flying wing and tailless layout. In tailless aircraft such as Lippisch Delta I and Westland Hill Pterodactyl Type 1 and IV, horizontal stabilizers at the rear of the aircraft are absent. Flying wings like the Northrop YB-35 are tailless aircraft without distinct fuselage. In these installations, the engines are either mounted in nacelles of the fuselage on tailless aircraft, or buried in the wing on flying wings, driving propellers behind the trailing edge of the wing, often by extension shaft. Ultra paramotor, powered parachute layout. Almost without exception, flex-wing aircraft, paramotors and powered parachutes use a pusher configuration. These craft run on flat surfaces, land, water, snow or ice. Thrust is provided by propellers and ducted fans, located to the rear of the vehicle. Hovercraft, lifted by an air cushion, such as the 58 passengers senior N6 airboat. Flat-bottomed vessels planing on water. Propeller-driven snowmobiles, also known as aerostats or aerodyne. Most produced, manned aircraft. Royal Aircraft Factory F. Rutan Canards varies and Long EZ, home-built and GT-1000 UAVs. AeroVironment HQ-11 Raven, hand-launched UAV 13,000 advantages. Practical requirements. Placing the cockpit forward of the wing to balance the weight of the engine aft improves visibility for the crew. Similarly, any front armament can be used more easily. The absence of front engine allows special equipment to be efficiently installed in the fuselage nose. Consequently, this configuration was widely used for early combat aircraft, and remains popular today among ultralight aircraft, unmanned aerial vehicles and FPV radio-controlled planes. Aircraft where the engine is carried by, or very close to, the pilot. Place the engine behind the pilot to minimize the danger to the pilot's arms and legs. Aerodynamic Pusher may have a shorter fuselage and hence a reduction in both fuselage wetted area and weight. In contrast to tractor layout, a pusher propeller at the end of the fuselage is stabilizing. A pusher needs less stabilizing vertical tail area and hence presents less weathercock effect. At takeoff roll, it is generally less sensitive to crosswind. When there is no tail within the slipstream, unlike a tractor, there is no rotating prop wash around the fuselage, inducing a side force to the fin. At takeoff, a canard pusher pilot does not have to apply rudder input to balance this moment. Efficiency can be gained by mounting a propeller behind the fuselage, because it re-energizes the boundary layer developed on the body. and reduces the form drag by keeping the flow attached to the fuselage. However, it is usually a minor gain compared to the airframe's detrimental effect on propeller efficiency. Wing profile drag may be reduced due to the absence of prop wash over any section of the wing. Safety. The engine is mounted behind the crew and passenger compartments, so fuel does not have to flow past personnel. Any leak will vent behind the aircraft, and any engine fire will be directed behind the aircraft. Similarly, propeller failure is less likely to directly endanger the crew. Leaks of fuel, oil or coolant from the engine stream away from the aircraft instead of becoming a risk to the pilot, other occupants, and any whole aircraft parachute installation. In case of a crash or crash landing, fuel and oil in the aft engine area are less likely to be a fire hazard, and high-energy propeller fragments are less likely to enter the cabin area. At the time when many military aircraft were pushers, the engine afforded some rear protection to the pilot. A pusher ducted fan system offers a supplementary safety feature attributed to enclosing the rotating fan in the duct, therefore making it an attractive option for various advanced unmanned air vehicle configurations or for small, personal air vehicles or for aircraft models. Disadvantages: structural and weight considerations. A pusher design with an empennage behind the propeller is structurally more complex than a similar tractor type. The increased weight and drag degrades performance compared with a similar tractor type. Modern aerodynamic knowledge and construction methods may reduce but never eliminate the difference. A remote engine requires a drive shaft and its associated bearings and supports, special devices for torsional vibration control, increasing mechanical requirements, weight and complexity. Center of gravity and landing gear considerations. To maintain a workable CG position, there is a limit as how far aft an engine can be installed. The forward location of the crew may balance the engine weight and will help determine the CG, as the CG location must be kept within defined limits for safe operation. Load distribution must be evaluated before each flight. Due to a generally high thrust line, negative pitching moment and sometimes absence of prop wash over the tail, higher speed and longer roll is required for takeoff compared to tractor aircraft. Main gear located too far aft may require higher takeoff rotation speed, or even prevent the rotation. The routine answer to this problem is to lower the nose of the aircraft at rest such that the empty center of gravity is then ahead of the main wheels. Due to the center of gravity often being further back on the longitudinal axis than on most tractor airplanes, pushers can be more prone to flat spins, especially if loaded improperly. Aerodynamic considerations. Due to the generally high thrust line, a low-wing pusher layout may suffer pitch changes with power variation. Pusher seaplanes with especially high thrust lines and tail wheels may find the vertical tail masked from the airflow, severely reducing control at low speeds, such as when taxiing. The absence of prop wash over the wing reduces the lift and increases takeoff roll length. Pusher engines mounted on the wing may obstruct sections of the wing trailing edge, reducing the total width available for control surfaces such as flaps and ailerons. When a propeller is mounted in front of the tail, changes in engine power alter the airflow over the tail and can give strong pitch yaw changes, propeller ground clearance and foreign object damage. Because of pitch rotation at takeoff, propeller diameter may have to be reduced and/or landing gear made longer and heavier. Many pushers have ventral fins or skids beneath the propeller to prevent the propeller from striking the ground at an added cost in drag and weight. On tailless pushers such as the routine long EZ, the propeller arc is very close to the ground while flying nose high during takeoff or landing. Objects on the ground kicked up by the wheels can pass through the propeller disc, causing damage or accelerated wear to the blades, or, in extreme cases, the blades may strike the ground. When an airplane flies in icing conditions, ice can accumulate on the wings. If an airplane with wing-mounted pusher engines experiences icing, the props will ingest shedded chunks of ice, endangering the propeller blades and parts of the airframe that can be struck by ice violently redirected by the props. In early pusher combat aircraft, spent ammunition casings caused similar problems, and devices for collecting them had to be devised. Propeller efficiency and noise. The propeller passes through the fuselage wake, wing and other flight surface downwashes, moving asymmetrically through a disk of irregular airspeed. This reduces propeller efficiency and causes vibration-inducing structural propeller fatigue and noise. Prop efficiency is usually at least 2 to 5% less, and in some cases more than 15% less than an equivalent tractor installation. Full-scale wind tunnel investigation of the canard route on Varies showed a propeller efficiency of 0.75 compared to 0.85 for a tracked configuration, a loss of 12%. Pusher props are noisy, and cabin noise may be higher than tractor equivalent. Propeller noise may increase because the engine exhaust flows through the props. This effect may be particularly pronounced when using turboprop engines due to the large volume of exhaust they produce. Engine cooling and exhaust. In pusher configuration, the propeller does not contribute airflow over the engine radiator. Some aviation engines have experienced cooling problems when used as pushers. To counter this, auxiliary fans may be installed, adding additional weight. The engine of a pusher exhausts forward of the propeller, and in this case the exhaust may contribute to corrosion or other damage to the propeller. This is usually minimal, and may be mainly visible in the form of soot stains on the blades. Propeller and safety. In case of propeller tail proximity, a blade break can hit the tail or produce destructive vibrations leading to a loss of control. Crew members risk striking the propeller while attempting to bail out of a single-engined airplane with a pusher prop. At least one early ejector seat was designed specifically to counter this risk. Some modern light aircraft include a parachute system that saved the entire aircraft, thus averting the need to bail out. Engine and safety. Engine location in the pusher configuration might endanger the aircraft's occupants in a crash landing in which engine momentum projects through the cabin. For example, with the engine placed directly behind the cabin. During a nose-on impact, the engine momentum may carry the engine through the firewall and cabin, and might injure some cabin occupant.